So far in the course, in the last few lectures in particular, we have been discussing about how to describe the working of a system using a truth table, and thereafter to convert those specifications or the truth table into a Boolean form, a Boolean logic expression which can be realized using some gates. And we have always maintained that while doing so, we have to ensure that the expression is in the most minimized form that can be realized using the least amount of hardware or least amount of gates, or rather the circuit should be simple. So therefore, one of the clear-cut ways to describe this is that if the final expression can be realized using least number of gates, that is definitely a sign of less complexity. However, there are indeed some cases where this notion of complexity can be very vague. So let us say I have two expressions. Let's say I have case 1 and case 2. I have an expression, let us say y equals a plus, or let's say ab plus cd. And in the second case, let's say I have y equals abc plus cde. Now, for both cases, we will need a total of 3 NAND gates. For both cases. So therefore, if we were to draw this, it would be something like this. And this is y. Whereas for case 2, it would look something like this. This is the realization of these SOP expressions using NAND gates. So both cases, you see, the requirement is 3 NAND gates. So therefore, it seems as though the complexity is almost equal. No. In that case, when you see, in those cases where the number of gates are the same, you can still differentiate the complexity by looking at the number of inputs per gate. Here the number of inputs is 2, here the number of inputs is 2, here the number of inputs is 2. Here number of inputs is 3, here number of inputs is 3, and here the number of inputs is 2. So therefore, total number of inputs each gate sees in the first case is 6. And total number of inputs each gate sees in this circuit is 8. So therefore, this is more complex. Why? Now, why am I talking and saying that more number of inputs means more complexity? Simply because while it may not be visible in the gate form, it will be visible in the form of transistors. So a 2-input NAND gate will look like this. 2 PMOSes. A 2-input NAND gate will look like this. 2 PMOSes in parallel and 2 NMOSes in series. These are the inputs and this is the output. Whereas a 3-input NAND gate would look like this. There would be 3 PMOSes in parallel because there are 3 inputs, and followed by 3 NMOSes in series. So if you compare the transistors, here there are 4 transistors and here there are 6. So obviously this is for a 3 input NAND and this is for a 2 input NAND. So obviously since the 3 input NAND has 6 transistors, it is more complex. So this solves the debate. So there may come, in fact there may come many such cases where you will see that the number of gates required for 2 expressions may be the same. But in that case you have to distinguish them as per their number of inputs, which will correspond to number of transistors which are inside. So therefore, if not gates, then transistors is one level deeper, which will tell you more about what is the complexity that is underlying. So having equipped ourselves with the knowledge of K-maps and truth tables and minimized logic expressions, let us now take a look at certain application circuits. Let us now take a look at certain application circuits. One of the first circuits that we're going to take a look at is to achieve the arithmetic operation of addition. So over here, the very first circuit we're going to take a look at is called as a half adder. Now the name might sound very strange, but bear with me. We are soon going to see why it's called a half adder. So a half adder is a circuit that can add 2 binary bits. A circuit that can add 2 binary bits. So let us say if I have this half adder as a block, there are 2 input bits A and B, and outputs are also 2. Why the outputs are 2? Because whenever I add 2 bits, let us say A and B, I can get 2 outputs. One is called a sum, the other is called a carry. One is called a sum, the other is called a carry. So therefore, let's call this first output as sum, the other is called as a C out or the carry out. So we can very easily make a truth table as we have done in the past. So 0 plus 0 means the sum is 0 and the carry is 0. 0 plus 1 means the sum is 1 and the carry is 0. 1 plus 0 is again the same. The sum is 1, the carry is 0. 1 plus 1 means the sum is 0 and the carry is 1. So, this is what the truth table of a half adder looks like. So, definitely what I can see is I can write the minimized expressions for each of the outputs, the sum and C out. I can construct K-maps and I can see that the sum is A bar B plus AB bar, which is very similar to an XOR operation. Whereas C out is equal to A dot B. In fact, you don't actually need to make K-maps for this because they will not be simplified, but this is what it is. So therefore, if I were to draw the structure using basic gates, half adder using basic gates. So therefore, if the inputs are A and B. So for the sum, it is nothing but the XOR gate. So I can draw an XOR. And we will need an AND gate. Sorry, this should be sum and this should be C out. So therefore, this circuit inside this dashed box is a half adder. As simple as that. So let us see how a half adder can be used in practice. So here we will say 1 plus 0 is 1. Carry is 0. Here 0 plus 0, sum is 0, the carry is also 0. Here 1 plus 0, 1, carry is 0, and 1 plus 0, 1, again the carry is 0. So this is how we get the answer. This is how we can do addition. However, the issue now comes when at any place of significance, either the 1st place or the 2th place or the 4th place or the 8th place, whichever. At whichever position of significance, there could be an operation where carry would be generated. So let us say, for example, so 1 plus 0 is 1. So here the sum is 1 and the carry is 0. However, for the second addition, 1 plus 1, the sum is 0 and the carry becomes 1. Now what should happen to this carry? This carry should go over here to the next stage and be added. So therefore what happens is, we actually in general may need a stage where we have to add 3 bits at a time. So you would need 0 plus 1 plus 1, which will give you a sum of 0 and again a carry of 1, which will again then go over here. This you will get 0 with a carry of 1. That comes as the answer. So effectively, whenever we are adding two binary numbers of any digits, here I have shown you 4 bits. In general, there can be 6 bits, 8 bits, 16 bits and more. But whenever we are adding two binary numbers, we have to be ready with the situation where we could be needing more number of additions than just 2. In fact, we have to be ready for the worst case of adding 3 bits. 2 bits given by the number and the third bit that is coming as a carry from the previous stage addition. Let me repeat this. Whenever we are adding two binary numbers of any number of bits, we have to be ready at any stage except the first stage, perhaps, because first stage, or rather the 0th stage, there is no carry, there is just 2 bits. But above the 0th stage, we need to be ready to do addition of 3 bits, 2 of which are given by the number, the 2 numbers, and the third bit which is coming as a carry which is generated as a result of the addition of the previous stage. Is that fine? So therefore, in general, we need an adder which can add not just 2 bits but 3 bits, and that kind of adder is called as a full adder. Therefore, now the earlier adder which we just saw was called a half adder, which can add 2 bits. However, we now need a full adder. This is our second adder circuit which we will see. A circuit that can add 3 binary bits. So I'll say 2 bits plus 1 carry from the previous stage. Right? So therefore, the block diagram will now look like this. The full adder will now have 3 inputs, 2 bits A and B. The third bit we will call as C in, that is carry from previous stage. But what about the outputs? The outputs will still be sum and C out, because no matter what we are adding, there will be one sum bit and one carry bit, even if there are 3 binary inputs. So this is what the block diagram of a full adder looks like. So therefore, let us draw the truth table. So now this becomes a 3 input truth table. So now 0 plus 0 plus 0, the sum will be 0 and the carry is also 0. 0 plus 0 plus 1, the sum will be 1 and the carry is 0. 0 plus 1 plus 0, sum is 1, carry is 0. 0 plus 1 plus 1. Now, this will be 1 plus 1 means the sum is 0, but we have a carry of 1. One plus 1, the sum is 0, but the carry is 1. Because this 0 does not really have any effect on the addition. 1 plus 0 plus 0, the sum will be 1 and the carry is 0. 1 plus 0 plus 1, it's like saying it is 1 plus 1, which means the sum is 0 and the carry is 1. Again, 1 plus 1 plus 0 is very similar to 1 plus 1, which means the sum is 0 and the carry is 1. And 1 plus 1 plus 1. Now comes the fun. 1 plus 1 means the sum becomes 0 and the carry is 1. So the carry 1 is there. But 1 plus 1, 0, that 0 is now added to 1, which means the sum becomes 1. This is what the truth table of a full adder looks like. So if we were to write the sum and the C out in the condensed sub form, let us say sum is sum F1 of A, B and C in, and that is having the minterms at 1, 2, 4 and 7. C out will be some other function F2 of A, B and C I n, which will have the minterms 3, 5, 6 and 7. Is that fine? So therefore, let us try to solve these K-maps and try to obtain the minimized expressions for sum and C out. So this will be C in bar and C in A bar, B bar, A bar, B, A, B and A, B bar. The numbering will be 0, 1, 2, 3, 4, 5, 6 and 7. So for sum, the min terms were at 1, 2, 4 and 7. So sadly, we see that this is a case where there is no possible grouping. So therefore, we have no other option but to write the sum just the way it is. So I can just say the sum will be nothing but C in bar, A bar, B, corresponding to this term. Corresponding to this term, it will be C in A bar, B bar plus C in bar, A, B bar plus C in A, B. Let us try to group. Let us try to group the C in and C in bar separately. So C in bar, the common terms are this and this. So in bracket we will see A bar B plus A B bar. Plus we will take C in bracket we will see A bar B bar plus A B. So do these expressions look familiar? Yes, as we have discussed earlier, this is nothing but A XOR B. Once again, please note that XOR is not simplification. XOR means you will still need large number of NAND gates to implement them. And this bracket A bar B bar plus AB is XNOR, which is also not a kind of simplification. But XOR and XNOR are essentially complements of each other. So what I can write is C in bar A XOR B plus C in A XOR B whole bar. Now suppose I call A XOR B as sum X. So therefore this expression would look like C in bar X plus C in X bar, which is like saying this again looks like XOR, that is C in XOR X. So I can write this in a commutative manner and I can resubstitute what X is, that is A XOR B. So the sum is nothing but A XOR B XOR C. So essentially the sum, very much like a half adder, is still following an XOR operation. If you recall, the sum in case of half adder was simply A XOR B, which we had obtained. Now, what about Cout? Let's construct the K-map. So over here, the min terms for Cout were 3, 5, 6 and 7. So 3, 5, 6 and 7. It's like this. So here I can make 3 groups. One group over here, the other group over here, and the third group this way. Therefore, let me call this as group number 1, group number 2, this as group number 3. So therefore, Cout for group number 1, it will correspond to AB, plus group number 2 corresponds to common terms of B and C in, and this corresponds to group number 3 is C in and A. Again, they are not very different from what we had seen in the case of half adder, because in half adder the carry out was A dot B. So it seems that even the carry out is an extension from the case of the half adder. So this is how we obtain the expressions for the sum and the C out. So effectively what happens is that if you were to represent them in the form of a logic diagram, you will need a 3-input XOR gate to get sum. But for C out, let us say we are trying to do them using basic gates, you will need 3 AND gates and 1 OR gate. So let us say this is A, B, then B times C in, and finally the third gate will be C in times A. And all of these will go into the OR gate, and this is C out. All right. So this is what the circuit of a full adder looks like. Just like how we did for a half adder, we have now extended it into a full adder. Now let us see how we can use the half adder and the full adder in adding any two binary numbers. Let us say, just to keep things simple without the loss of generality, let us say that we have two binary numbers, each are of 4-bit. So let us say I have two 4-bit binary numbers and you are given a task of designing a circuit to add those numbers. Alright. So now your job as a designer will not be easy. Now those 4-bit numbers could be anything. You cannot play safe and say that, okay, let us assume that there will be no carry that is generated. You cannot think like that, because if you are given the task of designing an addition circuit for two 4-bit binary numbers. Let us say you have to design this circuit for the computer processor. Then you cannot say that, no, my computer will be only that computer which accepts numbers without any carry. Then that is a very foolish design. You cannot hope to gain much with those kind of designs. Your design should be ready for anything. So therefore, you cannot take an example here. You have to assume that those numbers could be anything. So let us say there are two numbers. Let me show them bitwise. A3, A2, A1, A0. Where A0 is the LSB of the first number and A3 is the MSB. This corresponds to the first number. The second number, let us say, is B3, B2, B1 and B0, where B0 is the LSB and B3 is the MSB. So we have to add these two. So how do we go about adding them? So let us say we have something like this. This plus is actually addition. So therefore, we have to start like this. A0 and B0. So let us say the sum they generate is S0. and they could generate a carry C0 also. So that C0 will come over here, the carry from the first addition. Then you will do C0 plus A1 plus B1, which will give you the sum S1 and a carry also C1, and that C1 could come here. Now if the carry is 0, then it's good, but we have to be ready that a carry could come. Alright, likewise A2 plus B2 plus C1 will give you the sum S2 bit and a carry bit of C2, which will come over here. So every stage, what is happening is that the carry is being sent to the next stage. Finally, we will add C2, A3 and B3, which will give us sum S3 and a carry C3, which will form the most significant bit, because there are no further bits to be added. So therefore, this will be the result. So how do we do this? For the 0th stage, how many inputs are there? There are 2 inputs. So therefore, this will be a half adder. For the first stage, there are 3 addition inputs. So this will be a full adder, FA. Here also, it is this will be a FA. And for this will also be a full adder. Now, we know the circuits for the half adder and the full adder. So therefore, let us show how to do this. For the 0th stage, we will need a half adder, and whose inputs will be A0 and B0. The output of the sum would be S0, and the carry C0 will go to the next stage. So the next stage will be a full adder, as we have discussed. So the C0 from here will go to the full adder, but the other 2 inputs will still be A1 and B1. And the sum output will be S1. Next stage will also be a full adder. The carry from the second stage is C1, that will go over here, just like this. And C1 will get added with A2 and B2. And this is the sum S2. And last but not the least, that will also be a full adder. Over here, the carry bit which is generated from the S2 sum will go over to the last stage, and the C2 will be added with A3 and B3. Here the output will be sum S3, and the final carry will also be a part of the result, which is C3. So this entire thing is my result. So how many gates? How many gates will we need over here in totality? Half adder needs 1 XOR and 1 AND. Full adder needs 1 3 input XOR. But suppose I ask, let us say we know that for a full adder, the sum looks like this. In terms of 2 input gates only, how many gates will we need? We will need 2 XOR gates, which will look like this. Suppose let's try to standardize. This is A, B and C in, and this is sum. Let us say we are making a bill of materials with 2 input gates only. So this full adder will need 2 XOR gates. What about the carry? The C out is AB plus BC in plus C in A. So we saw that it will need 3 AND gates and 1 3 input OR gate. So again, in terms of 2 input gates, it would be 3 AND and 2 OR, because the OR would look like this now. So this will be AB, this will be BC in, and the third input, that is C in A, could be ORed in this manner. And this is C out. So we need 2 XOR, 3 AND and 2 OR. Likewise here also we need 2 XOR, 3 AND and 2 OR. Same here, 2 XOR, 3 AND and 2 OR. So how many total gates do we need? 2 plus 2 plus 2 plus 1. So totally we need 7 XOR gates, 9 plus 1 10 AND gates, and 2 plus 2 plus 2 6 OR gates, all of which are 2 input. So we need a total of 17 plus 6, 23 gates. Now that is a lot. For us, that is a lot. Why? Because for most of our circuits, no matter how complex we have seen thus far in the course, we have rarely gone beyond 5 or 6 gates. 23 gates seems a lot. And that too for doing such a simple operation like adding 2 binary numbers, each of 4 bits. So effectively, when you are doing an operation which is as simple as addition in either a calculator or a computer, the underlying circuit that is involved is essentially this: a circuit using half adders and full adders. So this essentially shows you that even a simple operation, after having solved K-maps, a simple operation such as this, even after having solved so many K-maps, would or could give you some results which have many gates. Now, had this not been simplified, we might have reached, like, let us say 30 gates, and that is even worse. Let us say we have reduced the number of gates from 30 to 23. But still, for us, this seems to be very boggling. It seems to be very mind-boggling, because this seems like a lot. If I now ask you to construct a logic diagram, you will sit and draw 23 gates, and that is just going to be a very tedious task. So what am I trying to explain through all this? I'm saying that even the simplest of operations in real life can have very complex circuits. So therefore, if simple applications themselves can result in very complex circuits, think what may happen if the application becomes more and more complex. If my number of inputs, outputs increase even more, the number of gates will definitely increase more. In that case, for us, the complexity will become too difficult to handle. Suppose we make a mistake in a K-map somewhere. That could be disastrous. So therefore, to handle more complex circuits, we ourselves have to evolve. We ourselves have to go a few steps above and beyond what we already know at this point of time. We have to go above and beyond from what we know at this point of time. So, in that step, when we are evolving ourselves, we have to assume, we have to think not from the point of view of a single gate, but we have to think from the point of view of much more than that. So far, we know that the basic blocks are defined, like the NAND gate, NOR gate, which are universal gates to realize most circuits. Although in this particular lecture, we realize a lot of the things using basic gates, XOR gates also. So the point I'm trying to say is that now we need to reduce our dependency on the gates and assume that we can in fact collect multiple gates under a single umbrella and give a name to that kind of circuit also. So therefore, we now need to think of bigger blocks or bigger logic blocks which are ultimately made of gates, but we don't really have to think too much about what are the gates that are inside. We have to assume that the gates that are in those bigger blocks are there and they're correct. So therefore, we now have to move to one step above, where we are dealing with silicon chips which have much more number of gates than we have used so far. And that will present to us a whole new world of opportunities. Why? Because if we don't have to worry too much about the underlying gates and we are aware of how those big blocks are working fairly easily, then using those blocks as a basis, we can build more and more bigger and complex circuits. And that is what digital design is all about in the modern days. To make circuits as complex as possible, to achieve operations or applications which are needed in this day and age. And we are going to look at attempts to do just that, but in the next lecture. Thank you.